Hey everyone, and welcome. I'm absolutely thrilled to kick off what I hope will be a fantastic journey into the exciting world of machine learning. And we're diving straight into a super practical and incredibly relevant project, house price prediction using machine learning. Have you ever wondered how online real estate platforms estimate house values, or how much your dream home might cost in a particular area? Well, by the end of this project, you'll understand the core concepts and even build your very own machine learning model that can predict house prices based on various features of a property. Every machine learning project, including this one here, begins with data collection. For our house price prediction, we need historical data on houses sold, along with their features and the final selling price. We'll be using a fantastic, publicly available dataset from Kaggle, a popular platform for data science competitions. It's called the Ames Housing Dataset, and it contains tons of information about past house sales. Every machine learning project, including our first one here, begins with data collection. For our house price prediction, we need historical data on houses sold, along with their features and the final selling price. We'll be using a fantastic, publicly available dataset from Kaggle, a popular platform for data science competitions. It's called the Ames Housing Dataset, and it contains tons of information about past house sales. We load our dataset using Pandas, a powerful Python library for data manipulation. As you can see from the df head output, our data includes various features like the living area, overall quality, number of rooms, and crucially, the sale price, which is what our model will try to predict. The df.info command gives us a quick summary. It tells us the number of entries, the data type of each column, and whether there are any missing values. This initial check is vital for our next step. Now, even before cleaning, we need to categorize our features. We identify numerical features, like the house's square footage or the number of full bathrooms, which are represented by numbers. And then we have categorical features, which are non-numerical, like the neighborhood, the exterior material, or the overall quality rating. Each type of feature often needs slightly different handling during preprocessing. Before we even think about building a model, it's absolutely essential to do some exploratory data analysis, or EDA. This is where we become data detectives. We use powerful visualizations to understand the distribution of our target variable, that's sale price, and see how different house features relate to the price. For example, here's the distribution of our sale price. You can see it's a bit skewed to the right, meaning most houses fall into a lower price range, with fewer very expensive ones. This kind of insight is super valuable, as it might suggest we need to apply transformations to our data later to help our model learn better. For instance, a logarithmic transformation, and this is a correlation heat map. It gives us a quick visual summary of the linear relationships between our numerical features and the sale price. Notice how features like overall quality, or GR live area, which is the above-ground living area, often have a strong positive correlation with sale price. This confirms our intuition. Generally, bigger or higher quality houses sell for more. This helps us identify potentially important features. To visualize this correlation even better, here's a scatter plot of GR live area against sale price. You can clearly see the upward trend. As living area increases, the sale price tends to increase too. This visual confirms a strong positive relationship. And for categorical features like overall quality, a box plot is excellent. It shows how the distribution of sale price changes across different quality levels. As expected, higher quality houses command significantly higher prices. These EDA steps are vital for understanding our data before we start building our machine learning model. With our data insights in hand, we move on to data preprocessing. This is where we create a systematic set of steps to transform our raw, messy data into a clean, numerical format that our machine learning model can understand. We use Scikit-learn's column transformer and pipeline tools, which make our entire workflow incredibly efficient and reusable. First, our numerical transformer pipeline. Here, we handle any missing numerical values by imputing them, filling them in, usually with the mean of the column. Then, we use a standard scaler to normalize the values. This ensures all numerical features are on a similar scale, preventing features with larger values from disproportionately influencing the model. Next, our categorical transformer pipeline. We also impute missing categorical values, often by filling them with the most frequent category. Then we use one-hot encoding. Since machine learning models work with numbers, one-hot encoding converts each category into a new binary column. For example, a neighborhood column might become multiple columns like neighborhood_east, neighborhood_west, etc., with a 1 indicating presence and a 0 absence. Finally, our preprocessor combines these two transformers using a column transformer. This powerful tool applies the correct transformations to the correct columns automatically. Now for the core of our project, model selection and training. Since we're predicting a continuous value, the house price, this is a specific type of machine learning problem called regression. For this project, we'll start with a powerful and widely used algorithm called the random forest regressor. It's an ensemble model that combines the predictions of many individual decision trees, which often leads to very robust and accurate results. Before training our model, a critical step is to split our data into two parts, a training set and a testing set. We do this using train_test_split. We'll train our model exclusively on the training data, about 80% of our dataset. Then, we evaluate its performance on the testing data, which constitutes the remaining 20%, and is data the model has never seen before. This is crucial to ensure our model isn't just memorizing the training data, but can actually generalize well and make accurate predictions on new, real-world houses. With just these few lines of code, we fit our entire preprocessing and modeling pipeline to our training data. The model learns the complex relationships between the house features and their prices. Once trained, we generate price predictions for all the houses in our test set using Model Pipeline Predict. But how good are our predictions? This brings us to model evaluation. For regression problems like house price prediction, we don't use accuracy or precision in the same way we do for classification tasks. Instead, we use specific metrics that quantify the error or difference between our predicted continuous values and the actual continuous values. The smaller the error, the better. Our key metrics are root mean squared error, RMSE. This tells us, on average, how far off our predictions are from the actual prices. In dollars, it's particularly sensitive to larger errors, penalizing them more heavily. For example, an RMSE of $25,000 means our predictions are typically off by about $25,000. Mean absolute error, MAE. This gives us the average absolute difference between our predictions and the actual prices. Also in dollars, it's less sensitive to outliers than RMSE, providing a straightforward average error. R-squared, or the coefficient of determination. This metric tells us the proportion of the variance in house prices that our model can explain using the input features. An R-squared value closer to 1 indicates a model that explains more of the variability in the data, meaning a better fit. If R-squared is 0.8, it means 80% of the variance in house prices can be explained by our model. While metrics give us numbers, visualizations give us a deeper, more intuitive understanding of our model's performance and behavior. Let's look at some important plots. First, the actual versus predicted prices scatter plot. Ideally, if our model was perfect, all our prediction points would lie perfectly on this red diagonal line. The closer our scattered points are to this line, the more accurate our model is at predicting house prices across the range. It gives us a quick visual check on how well our model performs across different price ranges. Next, we examine the distribution of residuals. Residuals are simply the errors, the difference between the actual price and our predicted price. We want these errors to be somewhat normally distributed around 0, with most errors close to 0. If we see a skewed distribution or multiple peaks, it might indicate our model is consistently over or under-predicting in certain price ranges. And then, the residuals versus predicted values plot. This is a very powerful diagnostic tool. If you observe a random scatter of points around the 0 line, that's generally good. It suggests our model is capturing the underlying relationships well. But if you see any discernible patterns, like a curved shape, or a fan shape indicating increasing errors for higher predicted values, it suggests that our model might be missing some important relationships in the data, or that its assumptions are being violated. This helps us refine our model further. Finally, for tree-based models like random forest, We can even see feature importances. This tells us which features the model considered most influential in making its price predictions. It's a fantastic way to understand what's truly driving our model's decisions, showing us which property attributes are most significant for pricing, such as overall quality or living area, often being at the top. And that wraps up our very first machine learning project, building a house price prediction model. We've covered the entire workflow from loading and cleaning messy real-world data to exploring its patterns, training a powerful random forest model, evaluating its performance with the right metrics and insightful visualizations, and finally, optimizing it further through hyperparameter tuning. This is a complete end-to-end demonstration, perfect for getting started in ML. If you found this video helpful and enjoyed learning about house price prediction, please give it a thumbs up. This really helps out a new channel. Also, don't forget to subscribe and hit that notification bell so you don't miss out on future videos, where we'll explore even more fascinating machine learning projects and concepts. I'm excited to continue this journey with you all. Thanks so much for watching, and I'll see you in the next one.
Please do like, share, and subscribe, and DM me if you need any help with your projects.